Okay, thank you everyone. So my name is Gomaa, and I'm a PhD candidate at the German Research Center for Artificial Intelligence, or DFKI for short, and the Saarland Informatic Campus, or Saarland University. And today I'm going to talk to you about our paper with Bilal Mahdy, sitting here, which titled Unveiling the Role of Expert Guidance. And I'm not going to put any distance, Ricky just mentioned it. So to start with this, I'm going to just quickly outline the talk. Okay. So first, I'm going to give some background and motivation for why we did this kind of work, and I'm not going to delve into details of this algorithm. I'm pretty sure that most of you are familiar with it, but I'm going to highlight an overview of each of them and the notable weaknesses that we found and why we are actually studying them and comparing them to each other. And then I'm going to talk about the methodologies that we use to do this kind of comparison, what kind of learning environment we had, what is the evaluation metrics that are traditionally used in this kind of algorithm, and how did we use it. And finally, I'm going to go with the results and give you some conclusion and tell you about our future work, or actually our current work that we building upon this one. Okay, so as we all know about reinforcement learning, it's training an agent by making it interact with the environment. So the agent do some kind of action, and then it gets from the environment kind of state, what's happening in the environment right now, but it also gets a reward, which is the most important thing in reinforcement learning. And the most complex problem with reinforcement learning is how to actually shape this kind of reward. So the reinforcement learning usually works with doing some kind of random action. It does this kind of exploration, like a human being when he tries out something by taste or smell, or actually by touching even, with getting a bad reward here. But the model is trying to, in the end, figure out what kind of reward you are giving it and maximize it to get the maximum possible reinforcement for the issue at hand. And so researchers had tried to work with different kind of learning, which is imitation learning. It's quite related. Behavior cloning is this form of imitation learning that goes all the way to 1990, actually. And it relies on expert demonstration. So instead of trying out the model, trying out in the environment back and forth, it actually gets some kind of demo, or let's say a video that telling it exactly how the others reacted to the environment that it tries to learn from this. And by doing so, it learns in a supervised fashion. So it takes the state in action as a pair and tries to predict the policy that it's seeing or it's already known from the user. So it's from the name, it's really quite straightforward. It's exactly trying to imitate what it's seeing. However, that's why it's very complex. It doesn't generalize well because it really tries to actually match its predicted power, so it doesn't work well during inference. And if there's any errors that happen during training, they really get compounded and happening also during the inference time. And so other researchers try to go to a different approach to imitation learning, but before talking about that, I'm going to give you an overview about GANs, which I think also you already remember or know. And GAN, the Generative Adversarial Networks, works with two competing models. You have the discriminator model and the generator model. And one of the models try to generate the policy, at least in the case of reinforcement learning, try to generate the policy or the data that you actually wanted to look like. And the discriminator is just trying to classify between this generated model and the actual distribution it has seen from the experts. And with that, it also try to teach the generator how to get the data as close as possible to this administrator. It also has a notable weakness, which is that adversarial methods or generation in general is not stable, as we know with something like hallucination in NLP, or having a very bad distribution for images from computer vision. Nonetheless, some researchers back in 2016, they created GALE, or the Generative Adversarial Imitation Learning, and they tried to use the powerfulness of generative AI to generate a model from the agent through this generator model without the need to craft a very complicated reward function, because they just gave the expert data from the expert policy on the right side here. And with that, they let the model itself try to judge its own performance and create its own reward for how likely it is to perform. And so we wanted to compare all these three methods together, because although some of them are super old and some are super new, we haven't seen so far some way of actually systematically compare to each other. So we created a highly known Unity game, which is a bird hunter game. It exists already in Unity, but we tweaked it to our own use case. And I think everyone's familiar with the game. We are trying to shoot a bird. And with this game, we had 3 levels of complexities. So we used a low complex environment, which is just having this image on the right, but only in grayscale. So you only see the black and white part. And then we added a medium complexity where we're using an RGB colors, like also you're seeing now with the blue or the red colors coming up. And the highest complexity is that we made it super complex for the agent, is that you have multiple birds coming out. Some of them give you a positive reward, some give you a negative reward, like the blackbird is resembling a bomb that appears sometime. Yes, it appeared quickly here. And this is also something that gives you a negative reward if you shoot it. We gave it limited ammo, so it needs to reload at some point. So all of this made the environment super complex, and we were able to judge it based on that. So before going to the results of our experiment, to explain the metrics commonly used in reinforcement learning and imitation learning techniques, of course, you look at the reward. Even if you're using an imitation learning, you still have some designed reward that you did just to evaluate it with. So the higher the reward you get is the better. And you look at also the episode length, so how fast you are in executing the task. So in our case, if you shot the bird from the first time, then you are super fast. If you missed a couple of points after shooting it, you get much less episode length. And the last thing is the entropy, is how consistent you are in this action. So we look at the actions that you perform and then see, even if you get a very high reward, in the future, will be you consistent in doing that, or you will do it much worse in inference time. And to look at some of these results, we start first with traditional reinforcement learning. So we look here at the most prominent 2 reinforcement learning techniques, SAC, which is a soft actor predictive technique, and BOPO, or the proximity policy optimization technique. And with that, we just judge them to see how they work with our environment, and also to see which one of them we could use in future experimentation. So we don't need to repeat all of the algorithms again when comparing to different techniques with reinforcement learning and imitation learning. So what we saw here is that SAC, so you can see in the top left corner, this is the reward. The blue and the orange, which the colors I think is not super easy to see here, but the blues and the orange are the PPO, and the green and the red are the SAC. And you can see that while both of them reach similar reward, both of them reach a similar number of steps at the end. And although the PBO has a better entropy, so remember entropy, if it's lower, it's better. So PBO has a better entropy than SAC. SAC is much faster in reaching these values. And so SAC is mostly more time efficient. And thus we use it in further analysis, but we could say something about those that SAC is already time efficient and more sample efficient, while BBO is more stable in the end. And then when we try to compare the imitation learning techniques to the reinforcement learning techniques, what we saw that, at least in the first stage with low and medium complexity, before going to a very high complex techniques, we saw that reinforcement learning is still performing much better than imitation learning techniques. And that's why it's still widely used until now, and no one moved to imitation learning yet. But we'll see later some different results for this. But judging with this alone, we can see that reinforcement learning has the best reward. It also has the best number of steps. But if you look at the bottom figure, it has a slightly higher entropy. It's a green curve. So at some point, it gets higher entropy than behavior cloning or behavior cloning and Gale. In this experiment, we use behavior cloning and Gale, not Gale alone, specifically because of the previous weakness I mentioned, where Gale is not stable and it didn't work alone at all, and it didn't converge in this low to medium complexity. However, we're moving to this very, very high complex scenario where you have the same actions, but the environment itself has so many states, like the multicolors, the multi-birds, the limited ammo. We saw different kind of results. And what we have seen here is that using reinforcement learning is still quite good. It's a green curve, but using behavior cloning alone, and that's this supervised learning approach, it's now very, very hard to actually converge or get anywhere. So it's going back and forth with the reward. It has a very bad entropy, very bad number of lengths, so it's basically not converging. However, what we see in that Gale and reinforcement learning, while they have quite similar reward and number of steps, maybe Gale has a better entropy. But what was really interesting, what we saw with this game, that reinforcement learning actually cheated the system. So what it did, because this is again with the complexity of designing the reward, is that it sat at a specific point here on the right and on the left, and as soon as the bird came out, it predicted from our own algorithms that the bird's going to come from this position and immediately shoot it. So this is a problem with our environment, that it was somehow predictable, and with our reward function that we designed, that it's, although the state is really complex, it somehow was able to manipulate it. And this is quite common with reinforcement learning, that it gets to manipulate or cheat the system. And so one of our conclusions, you can find more in the paper itself, but one of our conclusions is that imitation learning, while really specific to the expert demonstration, relies heavily on it. That could make it a powerful algorithm, but at the same time, it can fall as a weakness, as the demonstration itself is not that good, or something happened wrong during the recording of the demonstration. But it's more stable and it doesn't have this loophole. So it has no way of actually cheating the system, because it doesn't even get a reward from us anymore. While reinforcement learning, it can really have this cheating behavior, and although it's maximizing the reward, this is not our desired goal. And it can be very unstable in the prediction, so it not usually get a very good entropy, but sometimes you get a bad entropy that it doesn't realize or doesn't generalize well during inference time. We also saw that behavior cloning is not the best solution, which is also something that is confirmed with related work, that doing it in a completely supervised learning fashion is not working for such complex environments. And so we see Gale as a bridge between behavior cloning and reinforcement learning, and that's why we try to use it in future work. Just to give a brief about our current work, future work, since you might see that the complex environment of the bird hunter game is not actually that complex. We try to use this more into robotic field. So we look into robotic grasping, where we teach a robot how to grasp a certain object, like a bottle, a ball, or something. But here we have the simple notion of a cylinder. And what we're trying to do is actually teach it only on one part of the one object, like the middle cylinder or the large cylinder or the small, and then let it generalize to other objects as well. So the training data will only have one of those, and then it will be able to predict on its own the other objects, or how to treat other objects, how to grasp it with an anthropomorphic hand. Which again, I'm going to talk about that more tomorrow in the other one, so I'm not going to delve into details here. The other future work we are working on is into robotic surgery. So we are also looking into teaching robot, again, simulation, because that would be super hard with an actual robot, even if we have a kind of a phantom eye using this. So we try to teach a robot how to perform the first part of a cataract surgery, which is only the incision. You can see here a very small red circle around an incision part for the cataract surgery, and this is also the current work they're working on for this. Okay, so here's some of the reference. I hope I was exactly on time, and thank you very much for the questions.
Sorry, this is more just a curious question. With the shortcut on the version, what was it that the
So here, maybe it's not apparent in this snapshot, but when you go with the game for a very long time, we found out that the birds, at least in the algorithm that we did to actually generate these birds in a random place, they were not really random. So they were always coming from the same place, from the lower left corner or the lower right corner, and they're not coming from the top or from the bottom or anyway. And that's what the model has learned, is that it always comes from this, and instead of having this entire screen as a mixed coordinate where you can actually see the bird, because it has a computer vision for you to actually see in this pixel on the right, and instead of waiting to actually see the bird, it knows that the bird is going to come from the most right left corner, or the most bottom right corner, or the bottom left corner. And then just switch between these two positions.
many things were interpreted? See, like to work out the time short. Is it purely a case of observing the behavior, or ways of larger scale amounts moving on, say, from the fact to converge very fast with one steps?
That's a question. Now that I've learned more about the ability from physics, you could look into that, but as far as I know, there wasn't a direct way of looking into that. Even if you see the model conversion really fast, you will actually consider that it's a good thing and you not question this. Similar problems, that's why I'm saying this is known with the reinforcement learning cheating way. Similar problem happens also with data games. It's a basic thing everyone was testing reinforcement learning on. One of the data games was this person in the middle, and he's shooting enemies from the right and left. And the model has the actions to actually like move, shoot them, or it has a sword that cuts the enemy and then goes all the way. And this is a very, very famous video by YouTube where the agents stand exactly in the middle and very, very fast, just go left and right without actually knowing if an enemy is coming. So it's going this really, really fast, just basically hitting the building, so hitting the enemy before it managed to actually hit you. Although it's not doing anything except switching very fast between right and left. That's it. This is why people are looking into ways to actually mitigate that. And the usual way you do it is by designing a better reward system, because the model in the end will only follow what you give it as nothing else. It doesn't see anything else except.
Question on the slide.
Which one, sorry? Ah.
Yes.
Yeah, so yeah, maybe I skip that. So right now, one game in general works well if you have one constant. Even if the expert is giving all, or if you have multiple experts, somehow average also distribution. So it doesn't work with that. But here, multimodal also means that you have different kind of illustration, like video and sentence. So I cannot still struggle with that. There is another algorithm that also when is that? Student set is called info game. So it somehow would also cite its reference, but we didn't use that here. We are planning to. And also just to give it clear, most real agents, we have this implemented with its own, but it didn't make it as clear all the system. Thank you. Thank you. One more round of applause for our. Okay, we move to our second paper. This paper is beyond original research article categorization via Multimodal by Turrisi from the University of Genova.
Where is the presentation? Okay, hello everyone. I'm Rosanna. I'm from Machine Learning Genova Center in Genoa. Today we'll talk about my paper called Beyond Original Research Articles Categorization by NLP. A bit of background, motivation. So nowadays we are living a big increment of the number of published papers. Here you can see a graph of the numbers of papers published from 1956 to 2022. And in the last decades, we have an exponential increment of the literature. So this means that we need better tools to navigate the literature. We need a better recommendation system. And so the ultimate goal of this work is to provide better tools that tell us what are the similar papers, the papers that we may be interested in. So I think that you all know that we have a bunch of open access archive, such as PubMed, Internet Archive, and so on. One of the most popular, that is the one I will focus today, is Archive, and it contains. Slides are not visible online. Sorry, Thank you. Okay, so I was saying that Archive contains more than 1,000 scientific articles, and normally when an author submits a paper, is asked to assign a category label to the article based on a category taxonomy. So it means that we have a hierarchy with labels, and we have to decide what are the categories that mostly fit our paper. Of course, this procedure is time-consuming for the authors, but mostly important, it's restrictive. It is more based on sectors. So for instance, we may have two articles, the first one on artificial intelligence for brain cancer, the second one on statistical methods for brain cancer, and these two articles will be labeled as paper in computer science and statistics respectively, even if they both study brain cancer. On the other side, we may have another article on operating system, and this is actually a paper in computer science. So you see that paper 1 and 3, they rely on the same category, but they actually study two different things, while article 1 and 2, they both study brain cancer, but they are labeled differently. So that's why we want to go beyond this categorization. So this means that we want to find new categories, but we don't know how many, we don't know which ones. We still want to capture some information about the archive categories because they are not completely misleading, but we want to improve them somehow. How we want to do that? By using NLP. You all know, I think, what is it? It's natural language processing. It is a subfield of AI specialized in processing text. And more recently became famous because of training models, pre-trained models such as BERT. So this is the pipeline of the work. I used abstracts from archive dataset. Of course, I did pre-processing, then I used some text representation, and finally, I used a unsupervised approach to clusterize the papers into new categories. Let's start from the description of the data set. I used the archive data, archive articles published in 2023 for a total number of 43,853 papers. For each paper, I have the archive category. In total, we have 40 subject categories corresponding to 15 macro categories. An example of subject category is algebraic geometry, which correspond to the macro category of mathematics. Just a bit of statistics. The data is very unbalanced. For instance, the most popular subject categories contain more than 9,000 papers, while the least frequent contain 250 papers. Papers can be assigned with multiple categories. Here we can see that more than 5,000 papers have two labels. So, but if you are interested in, you can find more statistics in the paper. So the first step was preprocessing that consisted in syntactic parsing, lowercase text, lemmatization by excluding personal pronouns. I removed punctuation marks, stop words, edit tokenization, and all these steps we're doing by using Python package that is specific for scientific text. So let's go to the core of the work. The first question was, how do I represent my text? I investigated two possible representations based on SciBERT. SciBERT is mainly the BERT model that is trained on scientific papers. And I used two representations. The first one, SciBERT, extracts the last hidden layer of the first token, it stands for token. And the second one, CyberCLS, extracts the last hidden layer of the classification token. Then, after obtaining these two representations, I further process them, and I use two approaches. The first one is simply principal component analysis. Here, the idea is, okay, I have my embeddings, but they are high dimensional. So I want to reduce the cost of dimensionality and forget redundant features. So I used only the 95% of variance for each representation. The second approach is fine-tuning. This comes from the SciBERT paper. The authors claim that if you fine-tune your model on a downstream task, you will get a much better representation. So I did fine-tuning on the archive category classification. Now you may be a bit confused because I said that I want to go beyond the archive categorization. So the trick here is that I inserted a dense layer, the one in green. So my representation, the SciBERT one, won't be specific of the archive categories, as the last hidden layer will be the one specific for the classification, while in the SciBERT representation, I will just retrieve some information. This is exactly what we want. We want to retrieve information from the archive categories, but we want to improve them. Of course, I have to split the data into training, validation, and test. So these two are the approaches I further use on the SciBERT representation. So in total, I obtained 4 representations: PCA SciBERT, PCA SciBERT CLS, and FT SciBERT, FT SciBERT CLS. Just a bit of qualitative analysis. What I wanted to understand was if this representation contained information about the archive category. So here we are looking at 6 plots corresponding to the most frequent categories in archive. And in each plot we have in green, the papers corresponding to the archive categories. For example, in the first one, we have high physical energy phenomenology, and in gray we have the rest of points. So from this analysis, you can see that we have some clusters corresponding to the archive categories, but they're quite rough. And the same thing also for the other PCA approach with SciBERT CLS. When we use fine-tuning, instead we obtain a representation that has more information about the archive category, and it is expanded as we fine-tuned our embedding on the classification of archive categories. This is also for both FT SciBERT and fine-tuning SciBERT CLS. So now that we have our representation, the question is, how do I get my new categorization? I used a clustering approach, and specifically I used k-means on the training set. So here I don't know what is n, what are the number of categories. So I tried n ranging from 2 to 50, and I decided the best n by looking at the silhouette score on the validation set. So the silhouette score is a metric ranging from -1 to 1. -1 tells me that the clusters is completely wrong, points are wrongly assigned. 0 corresponds to overlapping clusters, and 1 to well-assigned and well-separated clusters. What I found is that when using PCA on both representation, I have a silhouette score close to 0, and it is in line also with the qualitative analysis I showed before. We have overlapping clusters. Instead, when using fine-tuning, I obtain a silhouette score close to 0.4. So this provides a better score. As the Cyber CLS provided the best score, I only use this for the further analysis. So the best n was found to be 32. So the interesting point is that the number of categories is between 15, that was the number of micro categories in archive, and 40, that is the number of subject categories in archive. So I found a new number that is in between these two. When using n equal to 32 and clustering my testing set, I obtain a silhouette score of 0.4. Here you can see a 2D projection by DSNet of the clustering, and points seems to be well clusterized. But the most interesting thing is the comparison between the categories I found and the categories in archive. So here I reported 4 clusters that are the clusters that are mostly populated in my clustering. And for each cluster, the number of papers for each archive categories. As you can see, we have for each cluster a few peaks. So it means that the archive categories are not spread across clusters, but what happens is that this method puts together a couple of archive categories. And this behavior is actually consistent with all clusters. So this table reports the most frequent categories, archive categories, within each cluster, and the clusters are ordered by frequency. So I don't know if you're familiar with physics, but for example, in cluster 31, we have that the 2 archive categories are general relativity and quantum cosmology and high energy physics theory. Now, I don't know anything about these topics, but I asked my colleagues that actually have a degree in physics, and they told me that these 2 topics are actually related to each other, and now authors working in one field actually work in the other field and vice versa, and also that most of papers may have multiple labels with these 2. An interesting fact is that, for example, in cluster 6, I have papers labeled with MAT-MP and MAT-PH in archive, but they actually both correspond to mathematical physics. So it means that this approach understands the content of the abstract, understands that these 2 categories actually belong to the same topic and collapse together in the same cluster these papers. The same things also for cluster 29, in which we have stat-th and math-st that actually corresponds to statistics theory, and in this case they are clusterized together. Another interesting fact is that archive categories can be split into different clusters. For instance, we have high energy physics phenomenology that is split in cluster 10 and 13, where the other topics are nuclear theory and high energy physics theory respectively. So it means that even if we have papers in one sector, this approach understands that there is another topic in that paper, so it splits the archive categories in 2 based on what is the other topic in the paper. So it means that this approach is most suitable for interdisciplinary work. So in conclusion, I investigated 4 text representation based on Cybert. I found that fine-tuning the Cyber CLS provides the best representation. I investigated a way to assign new categories to papers, and I found that new category and the number of categories is 32. This categorization still has information from archive taxonomy, but goes beyond it, as for example, a successful collapse archive categories labeling differently but belonging to the same topic, and I found that it's more suitable for multidisciplinary work. Thank you. About representation, right? Yeah. Yeah, so I have the abstract. Okay, for after proposing, I obtain a list of tokens. Okay, I use them as input for cybirds, and I have multiple outputs that are I have the hidden layer for each token, and then I have the classification token. So it is the output of cybird model. Yeah, I mean, I used both of them, or with PCA, or with fine tuning. So in total, I have 4 representations. Yeah. I use them for classic then, yeah.
The abstract, or did you when you use the keywords? Whether you like to
No, I just use the abstract. Actually, there is huge literature about what input to use, especially when you use a supervised approach in which you have the categories. A lot of work are on the full paper, some others are on the title, and this is an intermediate approach in which you use abstract, so you have a content of the paper, but it's not the full text. It is more advantage because most of the time you don't have access to the full paper. But I did not use the keywords because it's still a kind of labeling, and I actually wanted to have a real text for which you can retrieve the information and you can infer the label by yourself. Thank you.
Let's give a round of applause for. Okay, so we are finishing the last session of this morning. The last paper will be by Karen. It's titled Monitoring Cyber Peering, Team Learning, a Multimodal Human Development Approach.
Thank you.
15 minutes.
Okay.
Okay.
And the audio wasn't shared.
Oh, really?
Yeah.
The slides will be on.
I think my professor is on and he said he couldn't hear or he couldn't see the slides. Hi, good morning, everyone. My name is Karen DSouza. I'm a PhD student at Purdue University in USA. So today I'll be presenting a use case in multimodal AI where we want to monitor cyber peer-led team learning. So these are my professors, and this project is a joint collaboration with Purdue University and Indiana University. My professors also share joint appointments with both universities. So this presentation is a two-part agenda where I'll touch on the background, beginning with the current trends, and then I'll also touch on the problem statement and the summary in the second part. So let's get started with the background. It's important to know the current state in education right now. Last year, EDUCAUSE, which is an important global nonprofit, they published a report based on summaries of two-year data after the pandemic. And what they found was that we are beginning a very important digital era in education, where you can see the normalization of online and hybrid learning models, and this is the trend that which will possibly continue into the future. We're also seeing a transformation in higher education, and this is because of the requirement of flexibility with students, which form a part of our future workforce. Now, continuing with the report, there were two important social trends as well as technological trends that were focused on in the paper. Especially the part that we were interested in is the use of AI and big data in educational platforms. And then we went on to look at differences between active learning and passive learning, and this is where we really situated our research project. So when we look at active learning in classrooms, what we mean is mainly we look at interactive lectures, we look at brainstorming sessions, debates, large and small group discussions. On the other hand, when students are taking a class in passive learning, it's more an autonomous learning where the teacher or professor is simply speaking to the students without that interactive feedback. And passive learning is mainly teacher-centered. What's important to note here is that in our project, we're looking at active learning, which is the left side, because we want to know how we can stimulate the critical reasoning within students, and thereby capture that type of characteristic in our AI model. So the main active learning pedagogies that we studied were PBL, problem-based learning, where professors give students a use case and then discussions revolve around that. What we focused on is the middle box, which is PLTL, that's peer-led team learning. And then on the right side, we also see POGL, which is pretty popular in the US for deriving innovations within case studies. A little bit more about PLTL. So in the US, we have about, this is a conservative estimate, we have about 150 colleges and universities that actually employ this PLTL model, especially within STEM classes, for example, chemistry, math, computer science, and so on. So this is a pretty important educational model that we are looking to improve and put in AI. What is this PLTL model? So it's a two-part system. Students attend classes, for example, you can see the left side, we looked at chemistry classes. Students attend a normal lecture, and in the middle, this lecture is then supplemented by a peer-led workshop. So what that means is that if I'm registered for a chemistry class, I will attend the lecturing class, and then during the week, I'll attend one session within a group of peers. It could be 5 to 6 students. One peer leader will lead that group learning, and it's a very effective method of studying tough classes such as organic chemistry or introduction to derivatives in math and things like that. The motivation is that this collaborative learning actually boosts academic success, and this type of learning is found to be very useful for students that come from minority backgrounds, for females, and those type of characteristics. Again, just to give you an idea, for example, in this class, we could have, in a large enrollment chemistry class, I could have 400 students enrolled. And then, so those 400 students attend in-person classes, and then they also attend this peer-led workshop. So we could have about 40 different groups. On the slide, I'm just representing 5 groups. And then during the workshop, what's critical is that peer feedback is given by one student to another. And what I found as a student in my undergrad studies is that when I'm studying with a group of students, I tend to learn more. I'm not afraid to ask questions. And this is the fact that I want to capture in my AI model. Transitioning to an online version, which is what our project focuses on, I'm now moving towards a cyber peer-led learning. Everything stays the same, except that we are now catering to a more non-traditional type of student. What that means is when students are working full-time, they're not able to come into campus and attend these group sessions in person. So my professor, Dr. Varma-Nelson, came up with the cyber CPLTL model, which is a synchronous online version of PLTL. We're obviously offering more flexibility in the CPLTL sessions. Here's an example. So I attend the in-person class with my professor. So we have 400 students in class. At the same time, during the week, I can attend a Zoom class where I'm solving chemistry questions every week. So in a week, I could solve those 10 questions and try to learn with the students. The main idea is increased motivation and having a more positive approach. Now I'll move into the second part of the presentation where I'm going to start with the problem statement. So when I talked about these large student enrollment classes, the main problem is that there is a huge gap with receiving instructor feedback. Because there is no instructor feedback, students, for example, female students in chemistry or math classes, or even engineering physics classes, those introductory classes, they don't have a positive STEM experience. And this leads to a major drop in enrollments in schools such as the school that I'm from. And what we found, what my professor noticed, is that this one reason is that there is a lack of AI supported tools. And it was their idea to come up with this kind of a tool to support education. So here we have some statistics. 48% of students switched to a non-STEM field. This was a big survey that was released in 2019, where women and underprepared students were the most affected. And then further, 35% of these decisions were attributed to the negative effects of STEM classroom experiences. So my research question is, am I able to develop an AI model which could predict the quality of those online workshops that I talked about? The main problem here is, can I build this from small scale data? What do I mean by small scale data? We have in that, when you noticed in that CPLTL group, there's only 5 to 8 students. So that small video of 2.5 hours, can I derive sufficient AI insights from that? At the same time, can I use multiple modalities such as the text, the audio, the head, the facial expressions from those CPLTL sessions to develop that model? Our hypothesis is that we will be able to characterize a human in the loop model and rely on these multiple modalities. We want to look at behavioral patterns, the history. So I've been collecting data for the last 2 years. It's still very small scale data. It's not at all what we are used to, but that is my goal in this project. So then I want to go into a little bit of math. We decided to use what's called a student engagement index. This is something that my project deals with. So I'm looking at an aggregation of sentiment polarity from those text transcripts. I also look at audio features, facial movements, facial expressions, and head movements, and try and derive a multimodal fusion into that AI model. And finally, this is the framework that I'm interested in. This is what we built in that model. So on the left, you see these, the CPLTL Zoom videos. As I said, each video is 2.5 hours long. And then I derive 4 modalities, fuse the modalities into a model, and then I use active learning. So this active learning, let me just use a pointer. So this part here, the active learning, we decided to go with active learning because You may or may not know this, but active learning can actually work really well with small data and do a lot of work with that. It's a reiterative process where I choose samples based on uncertainty. And I could also use random sampling methods, but we decided to go with the least uncertain model, the least uncertain sample, go back, run iterations, train the model again, use human feedback for that labeling, and then try and monitor the CPL-TL performance. Just to clarify, what is CPL-TL performance? It's basically a score that a human expert gives to that CPL-TL model. And I'll show you in the next couple of slides what that is. Here's an idea of the initial findings that I've got. So here you see the blue sentiment score. For one particular session, the sentiment score dropped really low. And what I found is that when I looked at the lexical analysis, this drop in sentiment score could have been attributed to a low emotional state of the students at that point. That's one idea. Another idea could have been that it may not even have been related to the emotion. Maybe the text in that question that the chemistry students were solving, maybe the question was, this is a difficult problem, try and identify more difficult situations or something like that. So we didn't want to fully rely on that sentiment, but this is what the graph showed. Typically, when I talked to peer leaders to try and identify what other insights I could derive from this, if you look at the orange graph, so we started here low, but then we ended at a higher point. So peer leaders who are in charge of those group sessions, what they typically said is that this is how the progression of a class in a semester should be. And this kind of does, to a small extent, does show that the students were improving in their sentiment and they're more moving towards an independent type of study. Here's an example comparison that I used from, so this column here is my machine learning polarity. And then these three columns on the right are what I try to infer from ChatGPT's sentiment and participant engagement. So this is the comparison of large language models with my small scale machine learning polarity. I used Python in this case. So some insights that I could have received is that here you can see differences between polarities. For instance, the seventh group, my code said it was negative. On the other hand, ChatGPT sentiment said it was neutral. So I definitely need to dig into more of these insights in my future work. You can also look at the tone of the conversations in that workbook, and then professors using this can try and derive more insights. And then I can work more in NLP trying to derive insights on that text feature. A quick look at audio features. This is something which is pretty common when we build speaker diarization systems. These are the top 5 characteristics that I used. So I extracted 13 coefficients of MFCC and then these 4. So in total, I have 17 audio features. The challenges in the project are that there was a lack of labeled data. So this is what I meant by labeling those workshops. So we use subject matter experts to label those particular videos. So for example, one workshop 3, the subject matter expert said, oh gosh, this is not, this is a good workshop, but it could be better. What are factors that make it good, very fair, or very good? Are the participants in that workshop, are they collaborating? Are they speaking up? Are they using that critical reasoning within that learning session? So that's what we are looking at. Another challenge is the cost. There is a high cost to pay the subject matter experts to deliver. And then scarcity of data, as you can see from the slide, I only had very few labeling data sets. And then in addition, the data is multimodal. Am I able to correctly extract the video modes from there? So one idea is, in the multimodal data set, can I use text or audio, or text and audio, and build a model from this case? The second idea is, can I use that framework that I showed you earlier to derive those kind of insights and build my model. And we decided to just stick with 4 iterations. I used an SVM for the multimodal data set, and this is just groups of features. And then to end, my contributions were the framework where I used the multimodal data system set along with the human in the feedback loop. And I used the comparison between my machine learning code and the LLM. And I'm using an active learning technique to use both random sampling as well as the uncertain sampling. For future work, I definitely have to collect more data in the next couple of years. And then I want to improve session effectiveness to match the human expert label, and then try to reduce the workload. And then at the end, I want to increase STEM participation. And then I'm open to questions and also your suggestions for how I can improve the system. Thank you very much. Oh, oh.
Yeah. So there was time where you explained children. So my question is this human feedback provided by the subject matter expert, this is sort of like online learning that's going on.
That's a great question. So what I was thinking was, when I run one iteration, I'm going to stop the system and I'm going to build a GUI and then ask the professor of that class to rate the labeling of the feedback and try to compare the feedback with the human expert generated, the human expert label. Try to compare both of them. And if the professor agrees with the feedback, then that's fine. Just go through another iteration. If not, try to correct that label. So we're basically correcting labels. Yes. Yes, yes. So that's the idea that we had in mind. If you have any other suggestions, you know. Yeah, it is really interesting, and it's also very difficult because each professor has a different idea with their group. So, like, I haven't truly figured out how I'm gonna introduce that. Like, what then in that case, what would the accuracy be based off of? Like, one professor, like Chemistry 101, may not agree with Chemistry 102. Yeah, so I was just thinking of things like that. Yeah. Not the professor, yes. Yes, that's a good point. Yes. Yes. Yes.
So have a different model that, or one model is involved in that.
Gotcha. So actually what we did is we just used, so for now, currently I've used one model for just the sentiment and audio. So just one with no actual fusing the way that you call that. And my professor said to just use one model for all 4, try to generate the accuracy from there, and then build separate models for each of them and then fuse it. But the problem that we have is it's such small data, like I might only have 80 samples of data, and out of those 80 samples, I have to put in 60 for testing, 10 for, 60 for training, 10 for testing, and then validation. So how would that work? Like, I have to think about it a little bit more. Okay. Okay. Okay, I see. Okay, got it. So use the second approach first. I see, gotcha. Yeah, that's a good tip. Yes. Okay.
Or just go for
Yes, actually it's a two-part problem. So after COVID, students tended to prefer more the online, the CPLTL version, you know, for obvious reasons, because because they're non-traditional students, they're working full-time and they prefer that. But then I also looked at previous research papers that compared academic success of PLTL versus CPLTL, and it was similar, like it might have been like a 2-point difference or something like that. And that's when, and the thing is that during COVID, that's when CPLTL really took off because, you know, professors for a year, we couldn't come to campus, and they needed a secondary source. They needed actually a primary source to teach students. So that's actually what happened. Yeah. Yeah, but just to answer your question about how difficult the Zoom GUI is, so I actually have videos of Zoom. So it's like 5, so if say 6 students attended, so there's one Zoom window for the peer leader and then 5 small windows for the students. So imagine trying to capture that video data. So it's like 5 bounding boxes. Imagine trying to capture that over this 2.5-hour long video. So I tried to split it up as 15-minute samples. The sampling rate changes. Sometimes students don't have their webcams on. The whole complexity of that video, this video portion, where the head movement, right? So if the student bends down, I'm like, okay, the student is not engaged. Remember the SEI index. If the student is looking up to face the camera to engage with the peer leader, that's an engagement. Like, it's just so complex. I'm still trying to figure out how I'm going to design the head movements and the emotions, even the surprise or the facial expressions. Like, I don't know, like, can students be surprised when they're solving workbooks? I don't know. I also ran experiments to identify those 7 basic emotional standards, and I found only like ignorance, like only, you know, they're just completely blank because they don't do their homework before attending the peer session. Like, typically they're supposed to study and then attend the class so that the peer leader takes care of the remaining part of critical reasoning and things like that. But students these days, just like me, like, we don't prepare before class. So yeah, I have a lot of things to fix in this project. My pleasure.